So, should we start? Okay. Good morning, everybody. Welcome to the tutorial titled From Single Agent to Multi-Agent Pathfinding. It will be given by Nathan Sturtevant here and by myself. If the audience keeps in this size, then please feel free to maybe even come closer, and feel free to interrupt in the middle and comment, say your opinion if there is such an opinion or whatever. Want to say anything, Nathan? Okay. Brief schedule. So we are going to do introduction for the next 5 minutes, and then I will talk about optimal search algorithms, and then Nathan will talk about large-scale algorithms. Part A of our talk will be more of deepening into techniques and algorithms. Then we'll have a break, and the second part is going to be more of a survey nature, where Nathan will first survey explicit and polynomial domains and related algorithms, and I will survey multi-agent pathfinding problems and the related algorithms. Okay, we want to, before we even start to talk, we want to make a very important distinction, sometimes overlooked by people, between exponential domains and polynomial domains. Okay? So as an example, exponential domains, permutation puzzles, most of the planning problems that are used in the planning community are exponential, as opposed to polynomial domains. Examples are pathfinding in maps, GPS, sequence alignment, robotic arm that Nathan will show later, and many, many more. What's the difference between these two domains? So first, the input. Exponential domains are implicitly given because the graph is so large, no one can explicitly give you Rubik's Cube. We do not have enough time, and we do not have enough memory to generate this graph. As opposed to polynomial domains, which usually are given explicitly. Okay? Here is the graph, here are the nodes, here are the edges, and so on. Naturally, exponential domains have symmetries and internal structure in them. Okay? Not all of them, but many of them. This is why they can be given implicitly. Polynomial domains, it really depends. Okay? I can have a map of a city with absolutely no symmetries. It is given explicitly, and you cannot find any lines of symmetries or any kind of internal structure. The space size. So maybe the definition of exponential domains is that the number of nodes is O of B to the D, where B is a branching factor and D is the depth that you are going. Which means when I go deeper into the search space with some kind of a logical breadth for a search, I will see a factor of B more nodes at every depth. As opposed to polynomial domains, even if they do have branching factor of B, because they might have many cycles, if I do this logical breadth for a search, then the state space grows D to the K, where K is a dimension of the state space. Like a grid is, of course, the dimension is 2. So when I go to depth D, I see D to the K different states. And this, of course, relates to the number of states that I have. In exponential domains, a typical number of states could be 10 to the 15. The good old sliding tile puzzle, that's the number for it. Polynomial domains can be small, can be even as large as 1 million states, maybe even more. But because they are giving explicitly, then we have memory constraints on the size of the input.
But let me cut in here to say that there's lots of examples that violate that. So we'll talk about the robotic arm, which can be very high dimensional and very large as well.
Right.
So
this is
it's not universal, but it's
a very coarse. It's a very coarse division. Usually, at least research, when research focuses on exponential domains, how much time do we allow? Sometimes we allow days. Some people run, their algorithms for years, as opposed to polynomial domains where many times, because there are sometimes real applicable problems, you want to navigate somewhere, and so you want the path in the next few minutes, even less, like in games. Algorithms, usually for exponential domains, algorithms are DFS-based or IDA star, especially if I want to go much more beyond memory. While for polynomial domains, usually open list based or BFS based or A star based algorithm. This is, of course, a very coarse division, and there are many, many exceptions. Another distinction I want to make, and this is what we want our focus here to be, some kind of another very coarse distinction, which, you know, the division may be not as clear as I put it here, but, you know, I want to differentiate between the kinds of work that has been done on search in the planning community as opposed to the kind of work that has been done in search in the what is called the search community. So first of all, the domains in planning, usually the work is done on problems like the IPC problems, or they are giving some kind of a logic language, PDDL. They are usually exponential. In search, we focus both on exponential and polynomial domains, so this is why we sometimes use different techniques. Experiments usually, or, you know, a common important experiment that is done in the planning community is to see what can I do in 30 minutes. In search, we are not always committed to that. Sometimes I can run for years. I don't care. This is why memory restrictions in experiments in search is sometimes more of a big deal. Another cause to that, the memory issue, is that usually in the planning community, most of the time is spent on calculating heuristics. There are many, many very impressive and strong heuristics which take a lot of time to calculate. Therefore, you do not run out of memory in your experiments. While in search, sometimes we use very fast heuristics like Manhattan distance or octal distance or airline distance. So we process nodes much more faster and we need more memory. Therefore, in the planning experiments, usually A star is usually enough to deal with a memory issue. While, as I said, memory is a big issue in other types of experiments. Therefore, we should use either A star or IDA star because memory is out of, we are out of memory. So today, at least on the first half, we will talk on how to solve this memory problem in a sense. I will focus more on IDA star and exponential domains, and then Nathan will focus more on large-scale search, which is actually going to disk, and this is how it solves the memory problem. I turn over to Nathan.
Okay. So just wanted to say a word here. This comes from a paper we had a number of years ago, thinking about abstraction. And heuristics, at least when we're not, well, there's a complicated history between planning and search and things like that. But when we look at heuristics and abstraction-based heuristics, there's this huge difference between what you see in exponential and polynomial domains. So just sort of wanted to point out this difference really quickly. And so we have the Rubik's Cube on the left-hand side there. There's an abstraction. I'll talk a lot more about that in the external memory portion of the talk. On the right-hand side, there's an abstraction of a map that's being shown. And I'll talk more about that in the second half after the break when I talk about polynomial domains. So if we look at these two different types of abstractions, and we ask sort of what is going on when we abstract states, often what's being done is that we're virtually merging nodes together and creating a smaller graph. But the key from these techniques is that we're actually using distances in the abstract state space. So Rob's talk yesterday in the heuristic thing at the very, very beginning was talking about this. You know, we're looking at distance in the abstract state space, and we use those to give us heuristic estimates in the low-level search space. And this works really well in an exponential domain. So if you sort of have this analysis here, if it's growing as b to the d and my state space size, then b to the d is equal to n. And I want to say, well, I can't store that entire state space size, so I'm going to somehow make an abstract state space, which is f times smaller. Then if you push the math through, what you see is that the heuristic that I get in my abstract state space that's f times smaller is the original distance that would exist minus the log of f. And so what we see is that I can do large abstractions. I can reduce the size of my state space by a large factor, and I get a very small factor loss in the distances that I'm actually going to have in my abstracted heuristic. And so this is why you can take something like a pattern database, or this is what merge and shrink is doing as well. And you can get actually pretty good distances out of these in general for doing search. If you try to do this in a polynomial domain, actually it fails miserably. So again, if we look and do the same analysis, now we have d squared, for instance, in a two-dimensional domain. Then when I do this, I actually divide by the square root of how much I'm shrinking my state space. So if I'm dividing my state space by a factor of 4, my heuristics get divided by a factor of 2, which basically gives you a completely useless heuristic. So this is an example of a state space. This is only a fraction of it on the left. It had 11,000 states. When we divide it by a factor of 4, by doing this abstraction, and I'll show some examples of that later, we get down to about a factor of 4 reduction in states, and the distances are divided by a factor of 2. Now, you can just do weighted A star and multiply this by a factor of 2, and it'll work fairly well. But of course, then you're not guaranteed to be optimal, and that's that's a large, interesting, open question: is whether you want to be optimal or not. So this is just to say, at the high level, or to motivate you to stay to the second half of the talk today, after the break, is that there's massive differences in the way we have to think about exponential domains and polynomial domains and how we're abstracting them. And if you just try and apply techniques from one side to the other side, they're going to fail miserably. And so we're going to try every time we present something to talk about, hey, what happens if you try and do this in an exponential domain? What happens if you try and do this in a polynomial domain?
Okay.
Ariel, do you want me to time you?
Yeah.
We want to end you want to probably end around 9:30.
Okay.
Given that we started late.
Okay, so I would like to cover some optimal search techniques and algorithms along the lines that I described in a previous slide. There are 6 parts here. Probably I will not be able to get to the last ones. If I do, I will do it very fast, but I'll try to focus more on the first 3 and go very fast on the rest. If time allows, we'll see. So some introduction. So how do you improve search? Like I see the year 1985 where IDA star was introduced as some kind of a baseline, because it really made revolution to what kind of problems we could solve. Because you think about memories in 1985, I was alive at that time, and memory had 32K, was a decent size of RAM. So think about if you invent IDA star then, and hey, now we can solve very large problems which could not be solved before. Now what happened after that? Since then, better algorithms are, every day someone comes with a new variant of A star, or a new algorithm, and this technique, and this enhancement, and so on. And somewhere, I think in the 90s, so in fact, today I would like to talk more about the algorithmic part of new developments. But another line of work that has been done also very, very deeply and impressively in the planning community is developing smart heuristics. This is still going on now. In fact, Nathan will cover some of heuristics in his talk. I want to differentiate between offline task and online task. In an offline task, the computer works. The output is a path, and the task finishes. Now, an agent, a person or somebody else or a robot, whatever, can then follow the path or can not follow. It's beyond the scope of the search task, as opposed to online task where the agent is doing the search during movements. And there are many, many, many different scenarios, like real-time search, agent-centered search, navigation, and many, many types. I will focus today on offline task where the output is a path. We have many, many types of solutions: suboptimal, anytime, bounded suboptimal solution, near optimal solution. There is also PAC. I would like to mention this in a few minutes, but I would like to focus on optimal solutions, okay? Which means I must expand all the nodes that A star expands, whatever that means. We'll talk about this also later. And you know that we have to put in mind that search algorithms have a number of criteria. They should be complete. If it's incomplete, then very problematic. And then we have the trade-off, the natural trade-off between space complexity, time complexity, and solution quality. So we have to keep this in mind. Many algorithms were presented for non-optimal solutions to their different families and classes. Here is a fast list that I sketched. There are dozens more. Many algorithms, of course, this is also not an exhaustive list, have been done to speed up or to help A star in its derivatives in some sense. I would like to focus more today on those. And naturally, I would like to present work that I myself was involved in. And I chose those works which are as general as possible and maybe apply to exponential domains, to polynomial domains, and that are not domain specific. And I would like to focus on the general aspect of these techniques. Assumptions, okay? Unless otherwise stated, we are assuming an undirected graph. Okay? Some of our techniques apply also to directed graph with some modifications. Some may not, but we are assuming today an undirected graph. And also, usually I assume that the domain is exponential, if at least in my part of the talk. We will also refer to polynomial domains. Okay, so my first topic, I want to talk about the inconsistent heuristic. If you look at the third line, we have a journal paper, a very long one. It took us a lot of time to write the final version. And it's a summary of work that we have been done. We did like maybe in 6 years. Many people involved, 2 students, many professors, all summarized in a journal paper. So with about 50 pages, I will take 10 minutes to go over this briefly. So it was 5 years, 50 pages, and now it's going to be 10 minutes. Okay. And there is also some kind of historical perspective here. Inconsistent, if I'm going to tell you, hey, you're inconsistent, that sounds negative. Right? Nobody wants to be inconsistent, right? And indeed, in the books, Russell and Norvig write, it is hard to concoct heuristics that are admissible but are inconsistent. Korf says in one of his papers, almost all admissible heuristics are consistent. Okay, so heuristic sounds negative and probably, it's not there. What is the definition of a consistent heuristic? So everyone knows the regular definition of a consistent heuristic in the first line, some kind of the triangle inequality. But if I would like to focus on undirected graphs. If we are talking on undirected graph, it goes both ways. So the second formula here is also correct. If the heuristic is consistent by the same definition, then for undirected graph, let's come up with this equivalent definition. Okay, if both these lines are correct, then also the third line. And now there is more intuition into this. Okay, now a starting student or anyone can better understand what's going on. I'm saying, the difference between the heuristics of 2 states cannot be larger than the actual distance. If the heuristic has this property, then I'm consistent. It means that H cannot change more than what G changes when I go from a node to its child and back. Inconsistent if there are at least 2 nodes where this doesn't happen. Now, I would like to explain why is this inconsistent. Look at the parent here, okay? G equals 5, H equals 5, F equals 10. What does it mean F equals 10? This node says the path from the start to the goal through my node is at least 10. Okay? Now, this tradition must go to his children because any path through me goes through one of my children. Okay? Now comes a child who is distance 1 node more, and he says, my H is only 2, which means my F is 8. This is inconsistent with the legacy or the tradition of your family because your father said it's 10 and it must hold for you also. Otherwise, your father was not admissible. So if your father is admissible, don't tell me that you are less than 10. You're not saying anything. You're inconsistent with what we already know about you. This is, I think, a nice intuition about inconsistent heuristic. Yes? G is the true distance from the start to the current node. I think the correct definition should be the best known path currently from the start to the current node. Okay? No. The best currently known, yes. Okay. Another problem with inconsistent heuristics historically is the reopening of nodes. Here is a small example. All the edges here weight 1, except the edge from node D to node G in the right side, okay, which that weight is 5. The heuristics are inside the nodes. And of course, you see that node B is inconsistent with node D and also with node I. Let's see what happens. And this is an example that nodes could be reopened. The bolded nodes are those that are being expanded. So this node, start state is expanded, generates 2 nodes, A and B, with 0 and 5, with 1 and 6. A is expanded, generates C. Now C is expanded, generates D with F equals 3. D is expanded, generates G with F equals 8. Okay, now I expand node B. I generate D again. If I do not want to reopen it, then I at least move the parent pointer. It doesn't matter. I'm now, and if I do open it, and so at least I'm getting to this node twice, and now I will see the path of 7, which is the shortest path here. So node D is expanded twice with A star. Okay, that was considered a big problem when A star only existed, before IDA star existed. And in fact, this is a very old example from the 1980s of a graph. And it shows you an extreme case on a small graph where the number of node expansions, because the heuristic is inconsistent, and this is called the G5 graph because we have nodes from 0 to 5. This graph can be generated more and more. There is some special structure. Anyway, this graph, the number of nodes expanded here with A star because the heuristic is inconsistent, is exponential in the number of node expansions. Okay? So this makes inconsistent heuristic a very bad attribute because we are doing re-expansions, and it could cause you exponential blow up in the number of nodes expansions. Okay, now comes the good part. Part of our work, we did some theoretical analysis, and of course there was this worst case scenario of exponential blow up. But we have shown that it only occurs if edge weights and the heuristic values grow exponentially. But we proved that if all edges weights are smaller than a given constant, then A star will expand O of n squared. Like the bound is, so this exponential blow up only comes in very extreme cases, but in practical cases, if you can bound the largest edge weight, then you are polynomial. In fact, you are quadratic. So there is a blow up, but it's not as large as the extreme case. In practical cases, if you really want to know the details, the work took part of our group very long. A large number of papers with theoretical analysis of pages are in the paper. You're welcome to go into this and read. But this is the result. Okay, so inconsistency is bad, but the term consistent and inconsistent was coined before IDA star even existed. Okay, with IDA star there is no problem of node reopening because IDA star doesn't do duplicate detection, at least not in an explicit way. Okay, maybe with symmetries and so on, but it is unrelated to what's going on. It's not like there is an open list that I see, then oh, I was there, I was not there, and so on. Okay, so in a plain implementation of IDA star, every node or every path to a node is examined anyway. So if I go back to this example, node D would have been expanded twice with IDA star unless some very fancy move pruning or duplicate detection is done implicitly, not with an open list. Then D would be expanded twice anyway. So inconsistent heuristics do not cause a blow up in IDA star because this blow up is integral part of IDA star. So IDA star doesn't have to worry about inconsistent heuristics. It doesn't hurt him at all.
To add to that, it'll blow up the polynomial domains anyway.
That's right. IDA star, if applies on polynomial domains, it will blow up the state space anyway. And let me make another distinction between exponential and polynomial domains with this regards. Small cycles, okay? Polynomial domains, if you have small cycles and you do DFS or IDA star, it blows exponentially. It moves the domain from polynomial to exponential. This is very bad. However, in exponential domain, we're exponential to begin with. So if you have small cycles and I do not do duplicate detection, maybe my exponent will be larger. The branching factor might be larger. But I'm still in the class of exponential domains. So small cycles hurt, in this sense, hurt polynomial domains much more than what they hurt the exponential domains. OK, there is Pathmax. Everybody knows about Pathmax, which actually this bad child goes, correct yourself, behave yourself, don't say something inconsistent to your parent, which means inherit the f value of your parent. Because if your parent said that, through the parent the distance is 10 and above, this surely has also valid for you, then this is actually what Pathmax is doing. Now, there is a misconception, and it was highlighted by Rob Holty in his famous, here he comes. We are just talking about your misconception paper, and I would like to emphasize, and you are welcome to, you're encouraged to look into that paper. There are a number of misconceptions, and Rob says, here's a misconception, here's an example. One of his examples is that Pathmax doesn't make the heuristic consistent. It only makes the heuristic consistent along the current path. In fact, if you go, in this example, if I do Pathmax, it will still know D will be expanded twice because D will be F equals 6 only after B is expanded. But in the first time, it's expanded with 3 anyway. So Pathmax is nice, but it doesn't solve the inconsistency problem for A star. But let's talk about undirected graph and about IDA star. And we coined a method that we called bidirectional Pathmax. In fact, Rob, I think that the correct term should be any direction Pathmax, which means think about, look at the picture in white in the left-hand side. It doesn't matter where the search goes. Let's just look on the domain. We have an edge or a path of length 4, one heuristic of 10 and one heuristic of 2. What we can do, if the 10 is correct, which means there is no, the 10 is an admissible heuristic. There is no path to the goal smaller than 10 from that node. Now, its neighbor, which is only 4 steps away, says, well, my heuristic is 2. You're inconsistent with your neighbor, okay? The smaller heuristic should be at most 4 below the large heuristic. Otherwise, if 2 is correct, then 10 is not admissible. But because 10 is admissible, we can raise the 2 to be at least 4 below 10. And unlike Pathmax, which was done only in one direction, from parent to children, bidirectional Pathmax or any direction Pathmax, it doesn't even depend on the direction of the search. 2 neighbors, or if I have a large heuristic, I can then propagate this large heuristic all around as long as I decrease the edge weights. And if there was a heuristic there with smaller value, you can increase. So in IDA star, this works very naturally. Think about the left tree, and let's say that the threshold was 2, okay? And you have the root. So the root is expanded. It expands the left child, generated with h equals 5, f equals 6. It is pruned. We go back and we generate the left child. This left child has the heuristic of 1, f of 2, so we expand it. However, once we saw, and I'm assuming that the graph is undirected, once we saw the node with 5, and we use this BPMX trick, then the parent becomes 4. Because if your child is 5, you are at most 4, because you're 1 step away. If I am 4, of course, I can even go down to the right child and say you are 3, but in fact, with IDA star, I stop the search here, and the right branch is pruned, because 4 is already above my threshold. Okay, so I can save a lot of subtrees just by this. If I see one large heuristic, And in IDA star, everything goes naturally because I go to a child and I take an edge one way. When I backtrack, I take the edge in another way. I have heuristics of both sides. They can come with me as long as I decrease the edge weight by going. So with IDA star, BPMX works naturally. What about BPMX with A star? So this is more tricky. Why? Because in A star, I'm not necessarily visiting a tree along the edges. In A star, I have a node, I expand it, I generate the children are added to open, and now I can jump to a node where whatever node pops from open, it might be in the very other side of, there's no correlation, it's in another side of the tree. However, BPMX has a parameter of how deep do you want to go. BPMX1, it means I only want to go one level deep with correcting heuristics. And this is very natural for A star because when I expand the node, I have the parent and I have all its children at hand. So at least in this small tree where the parent is on top and the children are below, I can propagate values on these nodes that I already have at hand. So if for each child we set, for each child n, we set h of n to be maximum of its original value, and if h prime is the best child, then you are at least h prime minus 2. So for the parent, of course, it's h prime minus 1, and here's an example. 8 is the best child. It goes up to the parent to be 7, goes down to the middle child, and it's changed from 2 to 6. The right child was not affected because it was 7 already to begin with. Okay, but this is done naturally inside the search process. What if I want to go deeper? Okay, I can do some kind of look-ahead search and propagate heuristic values. I can do BPMX 2, 3, 4, which means I'm going deep, 3, 4, or infinity. So in our paper, we showed that this is very tricky. We have extreme cases where BPMX infinity, okay, go as deep as you can, could really, really help me a lot if I do this pre-processing before I'm expanding states. Just correcting the heuristics, it could save me from exponential blow-up. And we have another case where exactly the opposite happens. It was very nice without it, and it is catastrophic when you do BPMX. So you really have to be careful with BPMX and A star. But BPMX1 is usually, at least in our experiments, proved effective. Okay, now how do I find inconsistent heuristics? Here are 3 examples. Random selection of heuristics. This is now very popular. I have a large set of heuristics. Let's just randomize them or use one and then jump to another one. This could be inconsistent, which is good. You have diversity, and if you're using IDA star or A star, at least with BPMX1, heuristic can help you from one another. Dual evaluation, I'll not go into it. At the time, we were very fascinated by that. They are inconsistent. Compressed pattern databases, and in general, any partial heuristic is consistent because one node I can give more information from the heuristic, and on the other node I could be less informative, even if the original heuristic is consistent. So inconsistent heuristics are out there. I'm sorry? Maximum over a pattern database, I think, is consistent. Right? Or maximum over a set of consistent heuristics is consistent because I think it's not very hard to prove. You know, some results, just compare the line. First, you could see that, look on the 4th line, random. Random was inconsistent by itself because we had a number of heuristics and we chose randomly. It was much better, 10 times faster than using the same heuristic every time. When we add BPMX on top, we always got a very nice reduction. Now, what about BPMX in pathfinding? Nathan, I think this is where you want to say. These experiments were generated by Nathan, and he's here. Why don't he describe it?
Just it's a really important point here that when we add BPMX to IDA star here, what we see is like, if you don't do it, you're okay, and you're just a little bit better if you do it. So it gives us this nice enhancement on top. But the opposite exists in these examples. What you see is I'll point out what these lines are in a second when I get off the mic, but if you If you don't do BPMX and you've got an inconsistent heuristic, it can absolutely, completely kill you. And if you do it, then you can end up being okay. So the green line here is a reasonable, it's sort of it's an octile, it's sort of just a straight line heuristic. The blue line is the sort of theoretical best case that you could get, but it doesn't sort of apply here. And so the remaining two lines here, the red line says I'm going to use BPMX, and the gray line says I don't use BPMX. So this is an inconsistent heuristic, and it says this is an order of magnitude worse in node expansions over not using this inconsistent heuristic versus using it with BPMX. And so basically, polynomial in exponential domains, use it. If you forget, you won't get in that much trouble, but you just sort of lose a little bit of performance. In polynomial domains, use it, and if you don't use it, you're going to die a horrible death. We're not going to show the video here. I think we're short on time, but if you go to my website, movingai.com, there's some nice videos there, and you can actually see the difference going on. Or you ask me afterwards, I'll show it to you. We can show really clearly what's going on.
Okay. To summarize, inconsistent heuristics in BPMX, they work great and they are natural for IDA star and for exponential domains. They have a large potential for A star and polynomial domains, but you have to be careful. With inconsistent heuristics, you have this node reopening problem. So BPMX is tricky, although we got it to work, as Nathan said. If you do have inconsistent heuristics in polynomial domains, then sometimes BPMX 1 is your only choice, but this all becomes very tricky and problematic for A star and polynomial domains, and I think this is maybe the lesson to take home here. Okay, I would like to move to another technique, which is quite general. The history is that we had an algorithm that was called dual search. It was very complicated. One of the authors, Jonathan Schaefer, was always afraid it's so complicated, reviewers and other people will not understand it. But a lot in our minds, and then we came up with maybe a generalization or a better way to describe all this. And this is a very general technique that can be used on top of any specific algorithm. And it shows you how search can be done maybe in a more generic way or adds another dimension. So I would like to cover it. Let's talk about asymmetric heuristic. And again, I assume that the graph is undirected, okay? So the distance, if the graph is undirected, the distance between x and y equals the distance between y and x. But if the heuristic, okay, usually we refer to heuristic as, goal-oriented. But many heuristics, many simple heuristics, Manhattan distance, octile distance, just give me two states and I'll give you the heuristic between them. And a goal is just a special case of these heuristics. So think about that the heuristic is asymmetric in the sense, although we are measuring the same distance, the heuristic itself is not the same. If you want an example, Manhattan distance is symmetric, but okay, never mind. I was wrong in this example. Anyway, there are PDBs could be asymmetric if you do some symmetry lookups, and you look one way, you'll get one number. You look another way, you get another number. This was called in our old paper dual lookups. Anyway, asymmetric heuristics exist. If I have an asymmetric heuristic, I can look both those heuristics and take the maximum, because they are both admissible. They are both measuring the same distance. So this is some kind of preliminary to what I would like to say next. So single frontier bidirectional search, motivation. I will then describe the algorithm. Look at this tree, okay? You have f values inside the node, and let's concentrate on node C, where f of c equals g plus h, which is 2 plus 4 equals 6. Okay, so node C says, the path to me was already 2. My admissible heuristic is 4, which means I predict that the path through me is at least 6. Okay? Now, it doesn't matter what algorithm you are talking. Let's talk about what is the task now. Now, let's say that 6, let's say you are using A star, 6 now is first on open. Or you're in IDA star and you're in this node. You would like to expand this node. What is the task of this node? Okay? The task is as follows. Either find a path to the goal with a cost of 4, or announce that no such path exists. In this case, maybe you can give us a better lower bound, and because there are 2 other nodes, then we'll jump to these nodes. But this task of node C is very concrete, and the motivation for SFBDS, and in fact, maybe generalization or others, so the task is to close the gap between C and G. Can you close the gap? Or can you find a path from C to G of a length 4? Now, how does node C solve this task is independent of the tree, okay? I can change the algorithm. As long as I pass the answer, yes, I have a solution of length 4, here it is, or I say, no, I didn't find a solution, and I increase my bound to 5. How I do it is completely independent. In particular, the directions that I search, we are used to search from C to G, but this sub-tree, maybe I can reverse the direction of the search and search from G to C. As long as I pass information to my parent and to the tree in the same way, it is independent. It doesn't matter. It's a black box. Okay? So I would like to focus on this black box and suggest to switch the directions of the search from time to time, as long as it's a black box and I'm communicating my results to other parts of the tree. This is a motivation. So single frontier bidirectional search, actually the name is I'm using a regular search, but I'm switching my direction in internal nodes according to the current task, but I'm still communicating. This is why we call it single frontier, because it's not like a bidirectional search where you could see here is the wave, the search wave from this side, here is the search wave from this side. It's all in the same tree. And every node inside has to decide about what direction it goes. So I would like to differentiate between states in the state space, actual states, Portsmouth, Boston, whatever, and nodes in my search tree, but now every node has, actually it's a task. Close the gap between start and goal, okay? Of course, a goal state is a state where both sides are the same. If I want to close the gap between X and X, there's nothing to close. You're there, okay? Okay, in fact, look at the graph and look at the tree in the upper part. This is how we're used to span the tree here, okay? But if you think closely, look at node 1. Well, we say the search now arrived to node 1. What we really mean, look at the bottom, what we really mean is, okay, our task now is to find a path from node 1 to node G. However, if we continue expanding nodes only on the left side, then the task, or a special case of SFBDS, where you always expand the forward side, this is our regular search, we're actually thinking in the back of our heads on this tree. First, I wanted to go from S to G. Now I expand it, so now I want to go from 1 to G. I expand it, okay, so I want to go from 2 to G, 3 to G, and so on. But since the right part here is always G, we just do not spell it out. But it is in the back of our heads. So when we describe a search tree, usually we describe the search tree in the upper part. But what we really mean is we are goal-oriented if we are doing heuristic search. It's not a regular bread for search. We want to go to reach the goal. So we always have this right part in our head. Now let's go, while we know this, let's go into SFBDS. We have a node xy, which means I want to go from x to y. Here is the task of my node in the tree. Close the gap between x to y. Find a path or prove that there is such a path of this cost or declare that there is no such path. How do I do it? Now I have 2 ways to go. I can do the regular forward expansion, expand x and then generate x1, x2, and all the other children of x, and still I want to go from them to y. But I can also search in the backward direction. So x remains, but now I'm expanding y. So the nodes that I will get, the double nodes, okay, with start and goal would be x, y1, x, y2, and so on. Okay? So in the example we had here, I always chose the forward direction. But look on this specific graph and let's try to make different decisions. Here we go. So here I have my graph. It's exactly the same graph, and you have to compare actually this tree to the tree here. But now I'm using it in a more smarter way. I have SG. At the root, I expand the forward side. So now I have 1G. Now the task of 1G is what is the smallest path from 1 to G? And if I assume that the graph is undirected, here I'm saying, you know, I'm switching. We called it jumping based on how we did it in our dual search, the predecessor of this algorithm. But I'm switching to the other side, or jumping to the other side. Now I'm expanding from the other side. So node 1G, I'm expanding it from the other side. And the reason that I want to do it is because 1 has 3 children, or 3 neighbors, while 5 only has 2 children. So what I do, I'm sorry, G, I'm now at G. G only has 1 child. So why do I want to branch 3 ways if I can only branch 1 way? So 1G, we jump to the other side and we expand the backward side. The node that comes here is 1, 5, because 1 remains, and instead of G, I'm going 1 way above G to 5. Now I'm still expanding the backward side, so I have 1, 2, 1, 3, and in each of these subtrees I also expand the backward side. So the tree here is, you could see that in the end I have 2 gold nodes because the gap is closed between 1 and 1 and 1 and 1 on both sides, but the tree here is much smaller. Okay. In fact, what we need is what we call a jumping policy, or at every node you have to decide what side to expand. And once you have a concrete policy, some policies are, you know, we're doing it online or on demand, but whatever your policy is, if you follow this policy of which side to expand, this defines a complete search tree to search. Now, this search could be done with ID A star, any algorithm that you might think. So some properties. SFBDS is applicable, yes?
Is there a problem with reconstructing?
Okay, reconstruction of the solution path is very easy if you follow parent pointers in the tree. As long as you know which side you are, you maybe need 1 bit only to say, if I'm in the forward side, put it in this side of the path. In the backward side, I'm going to put it in the other way. But it's in the paper, we have a specific and concrete pseudocode to do it. Once you understand the algorithm, then it's really easy to understand how to construct the solution path. It's some technical detail.
You don't actually need to go all
No, I mean, look at the right-hand side node, 1, 1. All you need to know the parent, which direction it was. So I see 3, I'm putting it here. But when I go from G to S, from 1 to S, I know that it's in the other side. So you're just following it, and you're growing your path in both sides.
The question is, how do I know to look at that?
Keep 1 bit, which says I was generated from this side or the other side.
No. I'm telling you that, well, I have 2 nodes with 1, 1. Right?
Okay.
How do I know which of them to look at?
If you have 1, 1, that's a goal node. You stop. You have reached a solution. You are sitting on a path.
Well, I need to reconstruct from some way, right?
That's what I'm saying. If you are at a goal node, let's say the 1, 1 here, you go up the tree. All you need to know is whether I was generated on the backward side or the forward side to know, and only 1 bit sufficient for this. And then you place your node on either side according to what you have. Okay? 1 bit is all it's necessary. I have 5 minutes till the end. Wow. Boo. Okay. 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 Usually we have smaller search trees, but the performance depends on the structure so SFBDS is very tricky. Do not just use it. You have to be very careful and examine your domain to know that you have to know what you're doing. We have many jumping policies. The jumping policies that I just showed you is the branching factor. If I have two sides, expand the side with a smaller branching factor. It's a very trivial policy. We have JIL, expand the jump if larger. If the heuristic is asymmetric, you want to, and is consistent, then you want to expand the side with the larger heuristic. In the future, we'd like to add here meta-reasoning policies. We had good results. We also had limitations, usually in polynomial domains or on grids and maps. And the reason is because of duplicate detection. If you do it on top of IDA star, that's not a problem. But if you do it on top of A star, how do you do duplicate detection between nodes? Now, nodes are pairs. So if you have V states, you have V squared states. The amount of trivial duplicate detection will be much smaller, although we have some enhancements to that, but this is tricky. In addition, if you have dead ends and the shapes are irregular, which usually do not happen on exponential domains, at least not on the exponential domains we tried, then this can blow up the tree. With SFBDS, you have to read the paper to understand exactly why, but we showed examples where, especially if you have a dead end, you get there, if you jump to the other side, everyone will keep on generating this dead end, and it will just not be effective. So to summarize, it's great and natural for IDA star and for exponential domains, very tricky for A star and polynomial domains, and I have a challenge for you guys. See if you can apply SFBDS to planing domains. The intuitive reaction will be, we cannot do it. It's not really clear to me. We need to...
Most planing domains are not invertible. They have non-invertible actions.
Right. What you are saying is that SFBDS doesn't necessarily have to be undirected. It has to be, you could do reverse engineering it. Yes, Rob?
Yes, you don't need invertible operators. You need to be able to reason.
To reason, right. I think the challenge still, in fact, Carmel is not here. Once we met, he's from the north of our country, I'm from the south. We met exactly in the middle to discuss only this a few years ago. I think it's a challenge, despite what you are saying. Maybe you can formulate your domain such that you can do some kind of backwards reasoning. I don't know. Okay, how much time do I have? 5 minutes?
Yeah.
Who?
I have 30 right now if I start right now, so you can take 2 or 3 minutes.
2 or 3 minutes. I'll go very fast over the enhanced partial expansion A star. You know, A star is optimal in the number of nodes expanded. Let's say that I generated all these nodes. Surplus nodes, node B is the goal with f equals 3. What about node C and D? They were generated, they were inserted to open, but we never expanded them, we never looked into them. We call them surplus nodes. Now, if the branching factor is very large, you can have many, many, many surplus nodes, and this actually can blow up the search many, many times. Like in multi-agent pathfinding, branching factor could be exponential to begin with. So we want to avoid surplus nodes. There was an algorithm from the year 2000, it was called partial expansion A star, which says as follows. If my current f is k, I'm generating all the children, but I'm only adding to open those with f equals k. The rest are discarded, but I'm keeping track of them because the parent will now go with the best f value of the remaining children. Like this, okay? I'm generating all of them. These guys are discarded. The root now has 5 because it's the next child. And that's all, okay? Now let's say these are not the goals. Now I expand the root again, and so on. This is partial expansion A star. The problem with partial expansion A star that every time a node is expanded, we generate all the children. Some of them are being placed in open, some of them are discarded. We have found a way 2 years ago, we called this enhanced partial expansion A star, is that I generate, to begin with, only the nodes that I need. Okay? Those nodes that I want to discard, I'm not even generating them. So not only I'm saving memory, I'm only saving time. How do I do this trick? I have what we call operator selection function. This is a domain-dependent technique, which means it could, the idea is general, but you have to use domain engineering in order to build OSF. OSF says this: if I have a state P and a value K, please give me all the operators that will generate nodes with F equals K, and give me what's going to be the one after that. It turns out that if you do domain engineering, for many, many, many domains, you can calculate this in advance. You can calculate some kind of OSF, either as a lookup table or as a function, and use it. As a simple example, if you have a grid, you know in advance if you want to go northwest, then if you go north or west, the operator, the F will not change. If you wait, the operator will change by 1. If you go south or east, the operator will change by 2. So we showed a number of ways how to do those OSFs in domains and general directions, but you have to do domain engineering. It works very naturally with IDA star. It also has disadvantages, again, in polynomial domains. I will finish here just by saying, we have massive improvements many times with EPA star and EPE IDA star, but the limitation that you need domain-dependent engineering to come up with OSF, and it can blow up your open space, the open list, when you use A star, especially when you have many small cycles, such as polynomial domains, and we are keeping on saying this. Small cycles in polynomial domains is very bad. You have to be very careful how to deal with it. Okay, I had other subjects which I will unfortunately not be able to cover if we want to keep on the schedule. Nathan, please. Yeah.
And your phone. I use, well, either way. I can use it, sure. Okay. So we're going to continue the discussion of